projector is okay, thank you. So I see some of you first time.
Yeah, I just came from after the round.
I was here in first
No,
class.
and you also?
No, I was here in first class.
First class?
First class in the semester.
For the earthquake.
Because of?
I didn't come since the earthquake.
Hocam ben yüz yüze ders verdiğinizi bilmiyordum. Bir anda online'a baktım, geçen hafta yüz yüzeymiş. Sonra
Evet. İsminiz?
Cemile.
Ha, Cemile Hanım, tamam. Biliyorum, evet.
Geçen
Siz
sene
şeyde
yapmış.
katılıyorsunuz.
Bütün konferansa
Onları
instrument.
evet, tamam Cemile Hanım. So, we are going to continue from the last lessons, and we were talking about the. Nasıl çalışıyor? Tarzı bir şey. Evet. Bir şey.
Professor, about the homework, when will you get to know the dates of the homework?
The first one.
Homework.
Yeah, the first one. So we can know if we are solving right or not.
So homework, the first homework, what we need?
I mean, the first homework we want the answers, so we can make sure that we actually solve right. Okay.
What is answer?
You gave us 10 questions.
Yes.
And we solved them.
And you sent to me, and I will solve it.
Yeah, will you evaluate before the midterm?
No.
Before the final?
I will evaluate, and I will not give feedback.
Ah.
This is homework. It's not.
I mean, yeah, we want to make sure that it's right.
You can check. There are lots of literature, lots of possibilities. You can check. You don't need teacher. So. Okay. So this was the homework from the last week. So then let's continue. We were talking about the acceleration. Acceleration. How can you calculate the acceleration from momentum? In that direction, so
You can say.
okay.
السوداء مش السوداء
حرك هذه ما تقدر تصدق.
من جوا ايوه
Yes.
Hocam,
Okay, so keep it. So, okay, thank you. The acceleration. Yes, please.
hocam sesiniz çok uzaktan geliyor da bilgisayara doğru konuşma şansınız var mı?
Valla bilgisayara doğru konuşma şansımız var mı? Olabilir, deneyeceğiz. Tamam. Okay, so we discussed in our last lesson the acceleration for crank slider mechanism, or slider crank mechanism, crank slider mechanism. Now today we will discuss the crank slider mechanism for general 4-bar mechanism. As you remember, we discussed some in our previous lessons the velocity, and we discussed the relative velocity. How can we calculate the relative velocity if we know the VA, for example? Then we can calculate the VB. VB is equal VA plus VBA, V relative to A, and so that means the V relative to A. So we think also in the same direction to calculate the acceleration. You see here the vector polygon for the acceleration, and how we can build or create such a vector polygon for the acceleration, and what type of acceleration we have for the mechanism and for the 4-bar mechanism. So we will talk about the relative acceleration method dictates the creation of the vector polygons, and vector calculations can be used to analytically solve the problems. And like this equation, VB is equal to VA plus VB relative to A. So we can write the equations, vector equations for the acceleration, like VB normal components of the acceleration plus VB tangential components of the acceleration plus is equal VA normal plus VA tangential plus VBA normal plus VBA tangentials. That means in general, each point has two components of acceleration. One of them is the normal components, the other one is the tangential components we discussed in our previous lessons. So, and you see here the components, the normal component and the tangential component. For the A, okay, A we have all normal component, while the speed is constant. If the speed is constant, remember something right, is that right? All right. So here, the acceleration, normal component is A normal is equal V square over R, and this is R omega square, and AT is equal VB and is equal R alpha. You know, it comes from the V is equal V. V is equal R omega, and the VBT R. The alpha is the acceleration, the angular acceleration. So we learned all of them. Now we use here. So for them, if the point A, that means the crank moves with constant speed, that means there is no acceleration. So no tangential acceleration, normal acceleration. They have normal acceleration. So therefore, you see here the. Can I use that? Oh. And here you see therefore the normal components here. Huh? So this is the normal component. VAN normal component, and we know we can calculate this. We start with the member, the crank here, but we have to know the motion of the crank, because without knowing the motion of the crank, we cannot calculate the motion or the kinematic, any value regarding the kinematic or other leads. So therefore, let's say the crank is all beginning. I mean the RPM, rotation, and angular speed. And then since we know the angular speed, we know the distance, we can calculate the tangential speed. So it is known. So then we start to calculate the, like in the equations, to calculate the acceleration for the point B or any point on the coupler. So we start with the point A, and we know the velocity and acceleration of the point A. It is already given. So therefore, and we assume that the angular acceleration is 0, that means the speed is constant, so it has only normal acceleration. This is the normal acceleration. We know the magnitude and direction of the normal acceleration. So therefore, we can draw the vector polygon. We select a point here somewhere, and we can draw. It must be parallel to this line here. Parallel. Why parallel? Because normal components of the acceleration is collinear with the length a, let's say the a0 here. So it is maybe I have to write there a0. So it is difficult to a0. Okay. Here. So this is the A0, and this is B0 here. Let's write here B. Okay. Easy to talk about. So we know the motion of A0A, and there's only the normal component of the acceleration, therefore, and it is normal component. We know it is in the direction from A to A0. We draw a parallel from this. Can the scale, and then we can mark the magnitude of the normal components of. And regarding the BA normal and BA tangent and B tangents and B normal. So what is known, what is unknown? So this is we have to consider. So actually, we know the direction of the normal components for the point B and B relative to A. So the normal component of the component of acceleration must be collinear with AB and for B relative to B, and also collinear with BD0 for the point B, normal component, like we did it here, A0. And and tangential component must be perpendicular. Like direction must be perpendicular to, for example, the component of the acceleration for the point B must be perpendicular to BD0. It's also known direction. And also tangential components for B to the BA. So we know. But we know also, so we know also, we can also calculate this from point B, and like we have written here, the equations, we assume that VA is known. We are looking for BE. So calculate the BE, we have to calculate the B relative to A. So then B relative to A, actually using the vector polygon here, we know the VA is known. V plus V, so sorry, VBA we know, and VB is equal VA plus VB relative to A here. So that means easily, we learn in our previous lessons that we can calculate the velocity using the vector polygon. So since we know the velocities for the point B and B relative to A, we know the velocity, we can calculate the acceleration. At least we can calculate the normal for B, so for the B relative to A, and we can write B relative to A, where is it? Here, B relative to A, this is also, we know completely. And then, okay, VB must be tangential, must be perpendicular to that. And VBT also, VBT must be perpendicular to the B0. And normal component must be parallel to that here. And then drawing this vector polygon and using a scale for that, graphically we can calculate the acceleration. This is the boundary. We can use also algebraic way, and we can calculate analytic acceleration. Of course, for this position, graphically we can calculate only for this position, given position of the mechanism, like we did here in this example. Huh? So let's have an example and apply what we learned and think how can we solve it. The dimensions and configuration of the 4-bar mechanism shown in figure here are as follows. P1A, P1A is 300 millimeter, P2B is 360 millimeter, and AB is 360 millimeter. The same, okay. So, and P1, P2 is equal to 600 millimeter. The angle AEP1, P2 is 60 degrees for this position, given position. So, and the crank P1A has an angular velocity of, it is given 10 radian per second. Angular velocity is given for the crank, and angular acceleration of also given velocity and acceleration 30 radian per second squared, both clockwise. So turning clockwise. So then determine the angular velocity and angular acceleration of P2B and AB. P2B and AB. And the velocity and the acceleration of the joint B. So let's see what we have. First of all, we have to draw the mechanism according to the givens. And givens are, so VPA is of the given, the angular velocity, angular acceleration, and we are looking for B to B and must be wrong, and BAB, alpha AB, BB, and alpha B. So this is our mechanism. This is the position of the mechanism, okay. You know the P for the PA, and since we know that, we have to start from this point and we have to calculate it for the point B and B relative to A and so on. So what can we do first? First of all, we have to calculate the velocity. Because without velocity, we cannot calculate the acceleration. So the velocity is first thing. So we use a scale, 1 to 10, for the position of the mechanism. And we draw the mechanism, and then we know this acceleration and angular acceleration and the velocity of the link A, P or PA. So then we can calculate the VBA. So using the vector polygon, we know the velocity of the with PA, it is already given here. Because you know that, the angular velocity, times its length, give us the velocity of the point, as a total velocity of the point A, and this is the direction and the magnitude. So this is the direction and the magnitude. We can transfer here parallel to this point. So then we know the direction. We know the direction of the point B. Velocity, direction of the velocity of the point B. It must be perpendicular to that. So, and therefore, it is perpendicular. We can draw a line like this from the P2 in that direction, and we know the also direction of the velocity B relative to A, and this is this direction, and we can draw a line from the end of this BA, end of the vector BA, and they cross somewhere with each other, and the crossing point is called because this length gives us the velocity of the point B, and this length gives us the relative velocity, B relative to A. Also gives a scale, and with the scale we can calculate the value. dB is equal to 2.3 meter per second. dDA, B relative to A, is 2.2 meter per second. So since we know that, we can calculate the omega QB, that is this omega value, and we can divide 2.3 to this length here, and we can calculate the omega. This equation here, calculate the omega. This one, and we can calculate omega easily. So then we can also calculate the omega dBA. Like this is the dBA, the relative velocity 2.2 meter per second, and divided by this length. So we achieve the angular velocity of the point B, that is the big Q, and the angular velocity of the coupler, that is the B relative to A. So,
How do we calculate the PMEA? I didn't understand the QPM.
okay, so first, do you know how we can calculate the velocity of the point A?
Yes.
A, this is the, we know the angular velocity, and since we know the angular velocity, we can multiply with this length, and we can calculate it. That means we know that we calculate the magnitude, but we know also the direction, because clockwise, turning clockwise, so it must be perpendicular to this line, because this is a circle, must be tangent and perpendicular to this line. dA is already known. So therefore, dA is known magnitude-wise and the direction. So here we start to draw a polygon, vector polygon, and we start from this point, and I transfer the vector dA according to the scale here, and from this point, an arbitrary point, I draw the dA. Okay, so dA is known as direction and as magnitude. So what about the D and the B relative to E? I don't know the magnitude, but I know the direction. So the direction of dB is perpendicular to this line, dQ, because it is also moving like this. So it's a circle and must be perpendicular to this line. So therefore, I draw a perpendicular line from this point parallel to that. So perpendicular to that line, to this line, and this one. It goes like this. So, and the second line I have to draw for the velocity, I know the direction for B relative to A, and it must also perpendicular to this line. And this is the line here, and I is line from this point, and this point, and they cross each other. So I know the graphically, the velocities dv and b relative to e. So since I use the scale, and using scale I can calculate. Okay? So then the problem is, now how can I calculate the angular velocity regarding the point B and B relative to E? So using these equations here, B is equal to R times omega, I can check here. I can calculate the value of omega angular velocity. Is okay now? So the velocities, okay, we already calculated. Let's come to the acceleration. So how can we calculate the acceleration? So regarding the acceleration, we have to make a table like we did in our previous example here. So we have 3 bits, 1, 2, 3. The PQ doesn't move. It is grounded. So it doesn't move. This is the mechanism. So link 1 and link 2 and link 3 is shown. Link 1 PA, okay, link 2 is AB, and link 3 is QB. Okay. So what is known regarding the acceleration? We have to put into the table. So we know the acceleration consists of two parts in general, normal acceleration and tangential acceleration. So these columns show the tangential part of the acceleration, these show normal part of the acceleration. So let's start from the one here, from the one that means the PA. We know the tangential acceleration and also normal acceleration. Because we know all the values here. And if we come to the BA, AB or B relative to A, so here we know only the direction of the tangential acceleration. Direction means B relative to A, like this. The tangential direction must be perpendicular to AB. But we don't know the magnitude. Therefore, there's no magnitude here, only the direction. And normal component, do we know the normal component? Yes, we can calculate the normal component of the acceleration B relative to B because we know the length and we know the velocity. So velocity square over the length gives us the relative acceleration B relative to A, checks normal acceleration. Let's come to the QB. And for the QB, again, we have two components, or we have to consider two components of acceleration, normal and tangential. And regarding the tangential acceleration, we can know only the direction. Like it's here, direction tangential, because the tangential components of the acceleration must be perpendicular to this line. Normal component must be in line. So we can again calculate the normal components of that, and normal components below this square over R, and this, we know the BB, and we know the distance, and we can calculate that. So we have 1, 2, 3, 4 known as magnitude, as direction. We don't know the magnitude of AB and QB, but we know the directions. So then let's start to draw the vector polygon. And and this vector polygon you see here, we draw the normal components of the is one. So this is point here. Okay, we start from here. And first we have to draw then for the link one, then we have to show the normal component and tangential component, the normal component. So tangential component must be perpendicular to the PA. And where is it? So it is here somewhere. This is tangential component, and this is the normal component here. And then by drawing the lines from the end of this here, that direction for the must be parallel to the AB, because it is the normal components from AB, and perpendicular to that it is the tangential components of the AB. And then for the BA, the normal components is this one, and the normal component of the acceleration, and the tangential components is this one. And by drawing the lines at the end, to build the vector polygon, and using a scale from the vector polygon, we can measure and we can calculate the values, the quantities of the acceleration. So this is for example, here this is normal component PA, and the tangential component, this is the acceleration. This is the normal component. And the resultant is this one. This is the acceleration, total acceleration of the point A. And the same we can think for the B. B is the normal component, and this is the tangential component, so perpendicular to the line and parallel to the line. And we have here the acceleration, total acceleration for the point B, and B relative to E we have here. This is the normal component, this is the tangential component, and then the distance between A prime and B prime is the total acceleration B relative to A. Okay? So in order to understand it, or to let's say, to get used, so you have to do it, huh? You have to draw it, you have to work on that. Because it can happen that from the explanation or from the picture, from the discussion that we hear, it seems you can estimate that, okay, I understood, I can do that. But if you don't do it usually, so
Practice it.
huh?
Practice it.
Yes, practice. If you don't practice it, so it is difficult. Huh? So learning by doing, huh? This is the important slogan. Huh? Learning by doing, always.
Hocam,
Yes.
can I ask you a question?
Sorry?
I said in the second link, AB, shouldn't we multiply the 13.4 by the length of the link, 360 millimeters, to find the tangential acceleration?
Sorry, I couldn't follow that. Can you repeat it once more?
All right. I'm saying
Hmm.
to find the tangential acceleration for the second link, AB.
Okay.
Yeah. Shouldn't we multiply 13.4 times the length of the link?
We know the normal component. We have to calculate we calculate the normal component of the acceleration.
Okay.
So that means we know the direction and we know the magnitude. Huh?
Mm-hmm.
But we don't know the magnitude of the tangential part of the acceleration point, b relative to a. We know only the directions. After drawing it using the scale, we calculate this is 13 meter per second square, and this is 29.5 meter per for the QB.
I mean, why couldn't we do just as we did in the first link in PA? We calculated the tangential acceleration in link 1 PA. Why can't we do the same thing for the second link?
For the b relative to a, you mean?
No, I'm talking about you see how we calculated the tangential acceleration in link number 1 PA? Yes, this link. We calculated the tangential acceleration.
Yes, tangential and also normal component.
Yes, why can't we calculate the tangential for the second link as well in the same way?
But because we don't know that. I mean, you can, in order to calculate it, so tangential acceleration, that means dv, or we have to know the tangential acceleration of the link 2. That means b relative to a. We don't know that. We know we can only calculate the normal component since we know the tangential speed. Length times tangential speed gives us the relative velocity b relative to a.
All right, Professor. Thank you.
Please consider this table here. So what we know and what we don't know. We know for each component, generally we can say the acceleration consists of tangential and normal components. So this is the tangential part, this is the normal part. Huh? So here. So let's start with the link 1. And link 1, PA, we know the tangential acceleration, and we know also the normal acceleration. We can calculate because tangential acceleration is given and angular acceleration, angular speed, and the distance is given. So we can calculate, and we know also the direction of that. And therefore, for the link 1, we have no problem. But for the link 2 and 3, we can calculate using these velocity values we calculated before. We can calculate the normal components of the acceleration, but we cannot calculate the magnitude of the tangential acceleration for the link 2 and 3. But we know only the directions, and therefore we need the vector polygon by drawing to find out.
All right, I get it. Thank you, Professor.
Okay. So this is the, in very graphically how can calculate the velocity for a general for mechanism. So as I mentioned, this is one method, one of some of the methods. The other one is the analytical way and algebraic way. I will show you. And in the book, I give the name. So all these equations you can find there. There are also other possibilities. If you calculate the coordinates you learn in the dynamic part of the pneumatics, if you can calculate the coordinates of this point, that means the dx and the xb and yb, and first time derivative is the velocity. The second time derivative is the acceleration. It's also one way. But if you design something using the design software like Inventor or Workworks and so on, it is also very easy to draft such a polygon and find out the values.
Repeat that. Repeat that. I didn't understand.
Huh?
What do you mean?
I mean, if you make a design using design software like SolidWorks or Inventor, so you can using the gravity facilities, you can easily calculate for a certain position of the mechanism. You can calculate the velocity and acceleration. And to define a scale and to calculate it, it is very easy. I mean, if you use such a software. The facilities given by the software is actually fascinating today's. Okay, so this is another homework. You have to work on that, huh? So then let's, you didn't it? Huh? This is homework 7.6. Okay,
Hocam,
then
bugün 7
yes.
verdiğiniz bir homework mu?
Efendim?
Geçen hafta 7.5'i demiştiniz sadece de.
Burada şimdi ama bunu yapmadan öğrenemezsiniz. You have to do that in order to learn it. Huh?
Mail mi atalım hocam yoksa?
This homework is example 7.6.
Size göndermemiz gerekiyor mu hocam yapıp yoksa kendi başımıza?
Yes, I want to see it. Send it.
Okay.
Okay.
Hocam, when is
So
the
then-
deadline for the homework?
Huh?
When is the deadline for the homework?
Before the final exam. Okay, so
Hojab, can you show the question again, please, just to take a photo of it? 7.6.
okay. This one.
Yes, just a moment.
This length is not shown here. Sorry. Maybe given here, maybe 12 millimeter crank resistance, 6 radians is shown of the determine the acceleration of the link. 45. Okay. So, but I see the length is not given here. Something is missing. What's going on there? Why is not given? Must be given actually. So, nerede var mı? So let's 250, it could be 250. Bakalım.
Professor, is it possible to have all the homework questions in one PDF, just like the previous homework? Because we have many questions in different recordings, and it's hard to catch them up.
You send as PDF. What do you mean?
No. I'm saying, is it possible for you to make a one PDF that contains all the homework questions? Because we
No,
have
we
multiple
are-
questions in different
I
recordings.
did it at the beginning. So I did it at the beginning, but this is the last homework, huh?
Yes, I'm saying, can we do the same thing again?
And this is the single homework, huh? It's not more.
No,
But
but
I'm
there was a
not sure.
question from the previous lecture. There was another question, I think.
So it is finished already. I will not turn back again. Sorry. So please do this homework, huh? As homework, not this one, because the length is here not defined. Huh? So let's, I see now the length is here not defined here, the length here, and therefore I will check it. So please, as home, this one, you have all the dimensions. So the 44 crank rotates counterclockwise at 400 and is slowing down at the rate of answer. Determine the velocity and the acceleration of the 100 lengths. Okay, so. Hmm? Before the final exam. Yes.
Professor, can we bring the answer sheet to the final exam? Like formula
You
sheet?
have to send please with per email, huh? Send it per email.
No, the final exam. Can
Yes.
we bring formula sheet?
Not formula sheet. There's not too much formula. This is very simple. I'm like the kinematic. It's not machine design, okay, but not the other lessons.
Even in mechatronics components?
Mechatronic components, what do you want to bring? You didn't read.
No, I just remember.
No.
Hojam, but there are equations for the crank slider and the crank rocker. We have big equations and long equations. We can't. How are we gonna memorize those?
The equation, the analytic way. Okay, you have some equations there.
Like what level of the beat?
Okay, but per hand written. Also, I allow the equations. You bring the equations, but per hand written, and no solution. If I see any solution, so I will. Stop your exam, huh? All of them. So, okay, let's continue, huh? So, what can we learn more? Okay, this is the analytical way. Okay, we discussed. So, this is the algebraic solution for the command mechanisms. And algebra for the command mechanism, in this example, we have the crank slider mechanism. You know this crank slider mechanism from our previous lessons. So, we calculated position, you know that. Position, and we calculated also the we didn't calculate the acceleration. The second time derivative regarding these equations, of the equations of this one, also for the alpha angular acceleration, you can create these equations. This is the acceleration for the slider and for the angular acceleration. This is also another way we can calculate. And in example, I can answer question in exam. You can get the question. You have to write, and you check with the analytical. You check it's correct or not using the analytical equations. But you should also you must also know how you can calculate the acceleration and the velocity using the graphical.
But Hojam,
Okay, so
how can we make the graphical method enhanced, yani, without a system, without a computer? Handmade is
you know, at the beginning of this lesson, I said you need a compass, you need ruler, you need drawing equipment. Did I say? Yes.
You said.
Huh? I said, I know that. I know. I can show you. Huh? I know what I said. I didn't say. So, okay. And the second famous mechanism, our general four-bar mechanism, and also the algebraic solution for acceleration. I have here, and in your book, some of them are existing. I will position, I will calculate the position, acceleration, and velocity and acceleration. position, first time derivative, velocity, second time derivative is the acceleration. Okay, so then point on floating length. So it could happen that, or in the applications, that you should calculate the velocity or acceleration of any point on the coupler. Because you know the coupler is the most difficult part in for-power mechanism. Because coupler undergoes the planar motion. That means translation and rotation together. But the crank, let's say this one, is on rotating. Simple motion. And also this one is also a simple motion. It's also a circular motion at this point, and it's also the motion of the D is also a circular motion about this point here. But the coupler is different. So therefore, any point on the coupler, how can we calculate the velocity and acceleration? So this is the general equations we know from the relative acceleration or velocity method. And we can also, we know the velocity, I will get on the acceleration. The AX is equal, if you calculate the AX, and if we know the, let's say the AE, so AE normal plus AI normal plus AI tangential plus AX relative to I normal plus AX relative to I tangential. And also for any other point. So one of them you have to know, and the other one you can calculate using the relative motion equations. And like this here, it's the same. A is the acceleration shown a point AC here. Just give the point A, shift for C, point C, and acceleration. And we should know the acceleration for point B, normal, and plus this is the vector sign, plus acceleration B tangential, plus acceleration C relative to the normal, plus acceleration C relative to the tangential. Or the point A, you can write. If you know the acceleration B, you can use these equations. If you know the acceleration A, you can use these equations. Okay. There is shall we make a break?
Yes.
Okay, let's make 10 minutes break. Let's say 10, 20, 2:20 we start, huh?
Hojam,
Yes.
last week you gave us a homework, question 7.5. When is the deadline
Yes.
for that one? Is it also the final? Last week you gave
Also,
us homework.
yes.
Yes, when is the deadline for this homework?
Deadline before final exam.
For the previous question as well. Not this homework you
Yes,
gave
yes.
today, the one
Yes,
last week.
yes.
All right.
Before the final exam, okay?
examined, examined, mistaken omission,
Hojam, I'm sorry to interrupt you, but can I ask you a question?
So we can start, huh? The next part of this lesson regarding the acceleration, the Coriolis acceleration. Coriolis acceleration has been invented later, quite later. And I mean, technical calculations regarding the acceleration made the mistakes, certain mistakes, because scientists doesn't know about the Coriolis acceleration. Some guy, scientist, I guess from France, invent this part of the acceleration, and they try to predict it. So the okay, Coriolis acceleration it is present in a case when sliding contact occurs between two rotating parts, rotating links. Let's say we have so like two rotating, one here, rotating, the other one is here, rotating here, and they have a sliding. So here, this is a slider, here somewhere, and in this case, 2 to 4 bar mechanism. So here is 1, 2, 3, and 4, 4 by the way, 4 bar mechanism. And in this case, we have Coriolis acceleration. And so the especially the Coriolis component encountered in the relative acceleration of 2 points when all of the following 3 conditions are simultaneously present. And the 2 points are coincident but on different links, like this here. And the points on one link creates a path on the other links, and the link that contains the path rotates. So there is a nice example for that from the car. You see, each car has a door behind of the car, and the open and close of the door has such a mechanism. And this is like this actually. And in this case, we have Coriolis acceleration. So the and you know, from the relative velocity equations and relative acceleration equations and so on. And this is the Coriolis acceleration. B2 to B4, B2 to 4 times omega 4. Omega 4, this is the angular acceleration, angular velocity of the link 4. So we can calculate exactly. This is the equation. So the points are coincident, but not on the same loop. Point P2 slides along and places a path on B4, and the link that contains the path B4 rotates. So separating the relative acceleration terms into its component yields, we can see here in this example, and you see this is the point. You see the relative motion here between the slider and this part. This is rotating and it is sliding on that. And the point here is some headed then relative motion slider, and you see the Coriolis. So Coriolis acceleration. So the Coriolis acceleration. And you know, if you will not make an example, but you are going to there is example, and we can work on. If you cannot calculate correctly the acceleration, that means you are not also able to calculate the forces coming from the acceleration inertia forces. Then part of the force is not existing because part of the acceleration is not calculated. But as I mentioned, we have Coriolis acceleration in case that we have two things rotating and connected via the slider. Two rotating wings, like three and two is rotating about this point, and the other one is this point. So, and they are connected by the slider number 4. Okay, so we finished the part of the acceleration. I will CAM mechanism. So the CAM mechanism was that here. Maybe can show. Let's see whether we can find a
A cam and follower is a mechanism used to turn rotary motion into
huh?
reciprocating or back and forth motion.
Oh, you don't see that?
Reciprocating motion is different from linear motion because in a linear mechanism, you would have to reverse the direction of the input to get a different direction of travel at the output, while a reciprocating action goes back and forth while the input turns continuously. A cam is a wheel with an offset center. Cams can have different profile shapes that produce different motion paths in the follower. A snail cam produces a slow rise and a sharp drop. This kind of cam is not reversible in its direction. cam and follower is a mechanism used to turn rotary motion into reciprocating. A cam and follower is a mechanism used to turn rotary motion into reciprocating or back and forth motion. Reciprocating motion is different from linear motion because in a linear mechanism, you would have to reverse the direction of the input to get a different direction of travel at the output, while a reciprocating action goes back and forth while the input turns continuously. A cam is a wheel with an offset center. Cams can have different profile shapes that produce different motion paths in the follower. A snail cam produces a slow rise and a sharp drop. This kind of cam is not reversible in its direction. An eccentric cam produces a steady rise and fall in the output, like a sine wave. A pair cam produces a quick momentary rise and fall followed by a mostly stationary follower. The shape and must produce a back and forth motion in the blade, or in a four-stroke engine to control the opening and closing of valves that allow fuel to enter the cylinder and exhaust gases to leave. To enter the cylinder and exhaust gases to...
So, in internal combustion engine, we have a CAM mechanism over there to operate the valves, inlet and outlet valves. We use a CAM mechanism. So CAM mechanism is also important. Mechanism used in mechanical engineering. So that I can show more, maybe here.
Explain cam and follower. We know that in any engine, fuel is injected into the piston and combustion products are exhausted out from the piston by using valves. These valves are opened and closed with the help of a kinematic pair, cam and follower. The cam and follower are always in point or line contact with each other. So this kinematic pair is a higher pair. Cams are rotated at a uniform speed by a shaft, while motion of the follower is determined by the shape of the cam. Similar cam and follower pairs are used in sewing machines, feed mechanism of automatic lathes, etc. Thus, cam is a rotating machine element which gives reciprocating or oscillating motion to some other machine elements known as follower. Cams can be broadly classified into two types, radial cams and cylindrical cams. In radial cams, the follower reciprocates or oscillates in a direction perpendicular to the cam axis. Whereas in cylindrical cams, the follower reciprocates or oscillates about a groove in its cylindrical body in a direction parallel to the cam axis. Followers can be classified on the basis of the following three parameters: surface in contact, motion of the follower, path of motion of the follower. Surface in contact. On this basis, followers can be classified as knife edge follower, roller follower, flat-faced follower, and spherical face follower. When contact end of the follower has a sharp knife edge, it is called knife edge follower. Knife edge follower is seldom used in practice because the small area of contact surfaces result in excessive wear. When contact end of the follower is a roller, it is called roller follower. Here, due to the rolling motion between the contacting surface, the rate of wear greatly reduces. This type of follower is extensively used in oil and gas engines and aircraft engines. When contact end of the follower is a perfectly flat face, it is called flat-faced follower. This type of follower is generally used in automobile engines. When contact end of the follower is spherical in shape, it is called spherical-faced follower. This type of follower is used in automobile engine. On this basis, followers can be classified as followers in a due to uniform rotary motion of the cam. It is called reciprocating or translating follower. When the follower oscillates in a predetermined direction due to the uniform rotary motion of the cam, it is called oscillating or rotating follower. Path of motion of the follower. On this basis, followers can be classified as radial follower and offset follower. When the path of the motion of the follower is along the axis passing through the center of the cam, it is called radial follower. When the path of the motion of the follower is along an axis away from the axis of the cam center, it is called offset follower.
Okay. So, I hope you get some, let's say, some idea about the CAM mechanism. So let's talk about let me see that now. Okay. So CAM mechanism. So the input and output similar to the linkage. So you see here we have rotational motion and rotary motion. We have linear motion or reciprocating motion. But the behavior of this reciprocating motion, wait a little bit, then come down, and wait a little bit, and go up, and so on. This is other motion. It's an up and down, but the acceleration, velocity, and the position is very interesting depending on the application. And the important duty machines, different machines, packaging machines, chemical machines, aircraft, and some other machines. But today, we use it for the control the motion. But today, I mean, the mechanical equipment, mechanical devices to use for the for the control. Those they are interesting because the electromechanical systems developed for and take this place, the CAM mechanism, and much more quicker, much more flexibility occurs for the adjustment. But in some applications, we cannot completely replace CAM mechanism. So use it. And therefore, in these lessons, the part is the part of these lessons is the CAM mechanism. So the CAM mechanism, we have the input motion and the output motion. But the input is, let's say, the rotation, like here. So, like here, we have a rotary motion. Here, you see, it is rotating, but there is a CAM with the eccentricity, certain eccentricity, but it is not. The bearing is not in the middle, or this is not like a circle, ellipse, more or less. Therefore, there is eccentricity regarding to the center of the rotating part, and because of the eccentricity, the follower is going to move up and down. So they have two motions, input motion and output motion. This is input motion. Input motion is on the rotation. And generally, there is a motion with constant speed. Don't change the axis with the speed, constant speed, constant, let's say the angular speed. But the output motion is different. And we design a COM mechanism in order to create, to achieve the desired output motion. Use the input motion, the rotation, and the output motion is different. So according to the application or needs, according to the needs. This is the transfer function. The crank angle, so let's say from 0 to 300 the angle, and the follower makes such a motion. Let's say this is distance starts from 0 and goes there and stay a little bit there and go a little bit higher and stay there a little bit and go down. Like this. So this is an interesting transfer function between input and output motion. And this type of transfer function or the motion diagram we can create using the COM mechanism. And the output motion, we have to design according to the need. For example, let's say we have a certain linear motion, and it goes a little bit up and stay there for a certain time, and again it goes up, stay there for a certain time, and come down. And start again. Go one step forward and stay there for a certain time, and again go up there, stay there for a certain time, come down there, stay somewhere, and again. It depends on who we want. And this is the output motion graphic or transfer function. Transfer function. That means we transfer the input motion into the output motion, desired output motion. And you have seen also individuals engine valve control of the engine valve like this here. To open the valve, close the valve. No, it closes it by the spring. Spring close the valve. We open using this COM mechanism. If it is turning like this, and for this point, if this point meet this one, and push this slider down and open the valve. And in this position, so the spring push the slider up and it close the valve, and so on. That means interesting application to open and close the valve. These applications shown from the internal combustion engine, but there are also other applications use this type of mechanism. So here we have the mechanism like follower is rotating, follower is rotating, and here the follower is oscillating, or here is making the axial motion, and this is rotating the axial motion, this is radial motion, and so on. So depends which type of motion we need. So the problem is actually how can we design such a mechanism for a desired output motion. So here you see it's translating, motion is translating, shape is knife edge, you already learned here, and the pivoted and roller, like here, you get pivoted and roller. And the position is in, let's say, flat. Can differ. Inline or offset, or the shape wise, knife edge, roller, flat case, and spherical, and so on. And this is the picture from the application, you see the crank mechanism and the follower. Cam mechanism and the follower. Sorry. So we have to describe the motion at once. So translating cam must be rise outward for 25 millimeter in 0.7 seconds. Now we are going to define the motion, output motion. The translating comes, let's say here on the side, you see on the right side. Outwards, 25 millimeters. So that means go 25 millimeters in a 0.7 second, and about 7 then. Level for 0.2 seconds, level that means stay there, and then 0.2 seconds, and then fall in completely down 0.5 seconds. In complete cycles, how much time takes? 1.4. 1.4 seconds. In 1.4 seconds, the cam has to fulfill first cycle, right? First cycle. That means 360 degrees. Or 360 degrees. And during this 360 degree rotation, one cycle, the follower makes forward motion. Go up 25 millimeters, stay there, 0.2 seconds, and fall down. And the falling down takes 0.5 seconds. And this is very important. Describe the motion of the follower. You know, we don't describe the motion of the cam. We are describing the motion of the follower because this is the output motion. We will apply something. And in order to create such a motion, output motion, we have to design the cam accordingly. This is the art. So we have to design the cam in that way, or we have to design so the cam that the follower gives us this motion, the needs for our application. Now we will talk about how can we design the cam for a given description, motion description. This is the description of the motion. So I need an output motion is a linear motion up and down, and let's say we stroke from 0 to maximum 25 millimeters, and it will take 0.5 seconds, okay? And then we'll stay there 0.2 seconds, there's no motion, and then regarding the output, I mean the forward, then fall down 0.5 seconds. And no motion means, if there's no motion, that means the follower undergoes the circular motion, and so that there is no linear motion on the side of the follower. Compute required speed of the cam and convert the times axis to cam rotating angle, and the actual manner to achieve this displacement can vary. This is typically used for minimize the acceleration. Of course, we have seen in the video somebody is turning the cam mechanism and there's a follower going up and down. And the up and down motion
depends on the shape of the...
Yes, shape of the cam. Shape of the cam. And we have to also pay attention for the acceleration. The acceleration of the roller. The acceleration is not what we want. if possible, zero acceleration. Acceleration means inertial forces. Acceleration times mass, we have high force, inertial force, comes from the acceleration, and it is a big role for the machine. It is unbalanced force. And it creates a vibration, noise. And vibration means also and for material for the connections and all members of the machines. Okay. And so how can we define such a mechanism? Constant velocity, let's say. Constant velocity is for the static. Constant velocity, that means a certain time, certain distance. And rise means delta R, the time we use the distance over the time. B max is equal to h over t. A max is acceleration. Fall, you can calculate fall length times over the time, and then B max you can calculate, and A max you can. So this is the formula we can use.
H is the height. What is HT? If the H is for the height,
Height
what is
is
HT?
H.
For the duration, it is.
Yani, you see, use the time for the starting, say for going from 0 to the 25. How much is 0.7? Yes, is that.
So HT is in common stand. There is need to switch the dot.
Yes. For the rotation needs for that. So you can calculate, say, if you say for one cycle is 360 degrees. So, and we said the total time is 1.4. So 360 degrees. Sorry. 1.4 over 360 degrees. That means 10 degrees. Mechanism on an automated assembly machine, the cam must rise 20 millimeters with constant velocity motion in 3 seconds, level for 1.5 seconds, fall in 2 seconds with constant velocity. Second, that means here, so rise 25, somehow it's like this. Rise 25 with constant speed, and this is must be 25 millimeters, and then will stay there for a certain time, and then fall down, fall down, and also stay there, and start again. This is the one cycle here. One cycle. So we have to create such a motion. So determine the speed of the car. Use Excel to plot displacement diagram and calculate the maximum acceleration for that. So the follower motion is, you can, so you have for one cycle you have 360 degrees, and you have to consider, so the cycle time is given already, and cycle degree is one cycle for 360 degrees, so you have to calculate the theta is given already, delta theta is given 360 degrees, and time dt is already given, and you can calculate omega, and so we can continue. Huh? So then here you have there are some other examples, and at the end you have to design such a, this is just an example, come profile, and this is over here, and you need this is the eccentricity here, and this eccentricity actually the maximum slope of the rotating carriage. And this distance here is the maximum stroke gives by the followers. And here, let's stay for a certain time, and here also in that position, comes to this position, let's stay for a certain time, and in between fall down and up, down and up. Okay. So you are not responsible for this part of the lesson, for the time mechanism, but it is important. You have to study that. For understanding. For understanding, and you have to, and you will face later on if you work in design. The time mechanisms are used. So in the book there are examples. You have to study that. Any questions?
Are we having all the chapters included?
All chapters, yes. But not the time mechanism. I don't know because
Not this one?
Not this one. Not the time mechanism. It must be discussed more detail. I mean, I didn't have so much time for that, and therefore I take it out. Just for your information, but as the candidate mechanical engineer, so you have to study that. Okay? So, any question? So, Hamza, you come and go, huh?
I just arrived.
Just arrived?
Yes.
From your country?
Yes.
Interesting.
I was watching all this on my phone until I arrived.
Okay. Did you have a good trip?
It was good.
Okay.
It was in the north. I am glad that I came back.
Okay. We are also glad to see you.
Then,
Do you have any questions? Okay. Let me finish. That means at the end of the semester.
Have a nice semester with you.
Have a nice, and good luck for the summer. No, there's no lesson more about that. The exam starts next week.
if I happen to question, then I have.
Well, I don't know whether I have time. It's exam period.
I know because there's a short time period and a lot of subjects, plus it's online, you have to
I have more than 250 students.
Yeah,
Each of one send an email is really too much.
No, it's very
It's really.
Thank you.
But in the lesson, with pleasure.
Okay, no problem.
Okay?
Thank you very much.
Bye bye.
Yeah, I want to ask you. I have my first homework and second homework. My second homework, I got the information. I just have to write that. But I was like, should I give it to you face to face or?
What do you mean this is participate to the lesson?
Yes. The
I will not take care of it. It's not important for me.
Okay, so
You will come into the exam, but you will work very hard, for the exam.
inshallah,
Okay.
I will
Okay.
work hard because it was online. It was like for me hard to memorizing and understanding in online courses. Yeah.
Face to face much more better. So, by the way, we learned which method is efficient for the teaching and learning. Face to face is much more better
Yeah,
than
for sure.
online.
Like, it's easy to focus on other things, not on the topic.
Yeah.
And yes, the homeworks of the theory,
Homework. Did you make the homework?
I made them. I heard before I should submit it face to face or
Not by online. By email.
by email.
Yes.
Okay, my first homework is ready in my home, but I didn't send because I was thinking I should send it face to face.
No, by email. You have to send by email.
So,
Your homework.
so today, when I go back to home, I'll send everything the first homework,
Okay.
second homework, and we have just like first homework 15 questions and the second one question.
Today I give one more homework.
Do the students
Yes, to the
do
students.
them? I already see the record about
Yes,
it.
you can watch the records and you can see that.
So the total are 3 homework.
3 homework. Yes.
Okay. Today or tomorrow.
Did you make the homework, the machine design
Machine design? Yeah, I did it.
and static?
I finished aesthetics last 2 years.
Okay.
My brother still haven't.
Okay. Good answer.
I'm really happy to see you back.
Okay, thank you. Same to me.
Thank you.
Bye bye. Görüşürüz.
Professor,
Yes.
the cutoff time for the first homework is done. I had late registration. Can I still do it? Homework.
Moment. What? You are the homework you want to see?
No, I mean, I'm asking you, can I still do the very first homework you gave before midtime? What is it? Can I still do them? I had late
The voice, I
registration.
couldn't understand it.
I had
No.
late registration.
The voice,
The very first homework has done and submitted before I registered. That was after midterm. I'm asking you, like, can I still do it and send to you?
you mean the first homework?
Yes.
Hocam,
Did you send it, the first homework?
I'm
İlk
asking
ödevi
you,
hala yapabilir miyim diyor.
There are
do it and send to you?
Sorry, there are too much noise. So let's write what do you want and I will give answers. That write
Hocam,
as a message.
İlk ödevi hala yapabilir miyim diye soruyor hocam.
I could. Yes, you can do. Yes, you can do the first. You mean the first homework?
Yes.
You can do it. Okay.
Okay, thank you.
You can
very
do
much.
it, but don't send too late. Don't send too late, huh? So next week, latest next week, you have to send.
I'll send this Friday.
Okay,
Thank you very much.
it's okay for me. You are welcome. So,
Hocam,
any other question?
Hocam,
Ha.
Principles of
Evet,
Mechatronics sınavı çoktan seçmeli mi olacak?
Evet, aynen o şekilde.
Sadece o ders öyle değil mi hocam? Diğerleri normal, klasik.
Evet, o da şöyle.
Tamamdır hocam. Bir de statik ve machine design'da birer tane ödevimiz var değil mi hocam? Başka ödev yok.
Yes, onlarda bir tane vermiştim, evet.
Sistem
Başka
gibi.
bir ödev yok orada, evet.
Tamamdır.
Evet.
Çok teşekkür ederim hocam.
Rica ederim. Okay, next week we start with the exams. You have the 16th of May. You have, as far as I know, machine design 2, and 17 you have statics, and then 22 Principle of Mechatronics, and the 26, as far as I know, 26 is the Theory of Machines.
Yes.
Okay. Please be prepared well, and I wish good luck during the exam period.
Thank you.
Bye-bye.